Hello students, today we will going to see the primitive matrix. In the previous classes, you have seen different types of matrix, that is A cap, A, incidence matrix, bus incidence matrix and all. Those matrices are related with elements and nodes. Incidence matrix is element to node matrix and bus incidence matrix is with the element to the nodes which is not having reference nodes. Today we are going to see the primitive matrix. Actually, primitive matrix is element to element matrix which gives the complete details of an element. This matrix contains complete information about the network connectivity, the orientation of current, the loop and cut sets. However, these matrices contain information on the nature of the element which form the interconnected network. The complete behavior of the network can be obtained from the knowledge of the behavior of the individual element which makes the network. Along with the incidence matrix, an element in an electrical network is completely characterized by the relationship between the current through the element and the voltage across it. So mainly these primitive matrices are going to give the details of an element, how it behaves. Depending upon its characteristics and behavior, we are going to give the primitive matrix. See, this figure shows the primitive impedance matrix. The primitive impedance matrix can be given in two forms, either in admittance form or in impedance form. One element means it is connected between two nodes. Say from node P to Q, one element is connected. Then we are going to call that element as element PQ. In other words, an element is connected between bus number 1 to bus number 2. Then element is 1 2. Or an element is connected from number 1 node to number 3 node. Then element is called as 1 3. Like that, here we are taken P and Q, and the voltage at the node, like what potential difference at the node P is taken as EP, and at node Q is taken as EQ. The element which is connected from P to Q, that is element PQ, is having its internal voltage of EPQ and its impedance of ZPQ, what we are shown here. And the voltage between or voltage across the element PQ is given by VPQ. It is the difference of the two potentials at P and Q, that is VPQ is given by EP minus EQ. Next, this is primitive admittance matrix. Here you can see the same element which I have taken connected between P to Q, but it is shown in admittance form. In the previous one, it is shown with its impedance. Now in this figure, we are going to show with its admittance. Apart from the voltage source or internal voltage source in the impedance form, here we are going to use the internal current source, that is JPQ current, and IPQ is the current which is flowing through the node P to Q through this element, and ZPQ is the current source. The network performance can be represented by using either the impedance or the admittance form of the representation, as I told you. With respect to the element PQ, we can note down what are the different notations. VPQ, voltage across the element PQ. You are seeing this one. See, VPQ. That VPQ is nothing but voltage across the element PQ. And EPQ, EPQ is the source voltage in series with element PQ. This EPQ we can going to take it in only impedance form. That is what source voltage in series with the element PQ. IPQ is the current through the element PQ. You are seeing this one. See, IPQ in this one. Here also IPQ is flowing through the ZPQ. Okay. Next, JPQ. This you are going to see only in admittance form, where source current in shunt with the element PQ, and ZPQ is the self impedance of the element PQ, and YPQ is the self admittance of the element PQ. Fine. We are going to see the performance equation. Two forms, as I told you, one is impedance form, another one is admittance forms. In impedance form, we can write VPQ plus EPQ is nothing but ZPQ IPQ. Come to this figure. See here. Here VPQ is given. VPQ is nothing but the voltage between P to Q, and internal one voltage is there, that is EPQ. Addition of those two voltages, that is VPQ plus EPQ, is nothing but it's a drop of IPQ and ZPQ. Same thing we have written here in the impedance form. Coming to the admittance form, sum of the current IPQ plus JPQ will be giving you YPQ, VPQ. See here in this figure. Here IPQ is the current coming from the EP node and JPQ is the current source. Addition of these two current is nothing but IPQ plus JPQ. That is nothing but it's same as YPQ into JPQ. YPQ into VPQ. Okay. Thus, the parallel source current JPQ in admittance form can be related to the series voltage EPQ in impedance form as per the identity we can write it as JPQ is equal to minus YPQ EPQ. Instead of JPQ we can write it as minus YPQ EPQ. Continue with this performance equation. A set of non-connected elements of a given system is defined as primitive network, and an element in it is a fundamental element. It is not connected to any other element. The whatever equations shown previously, if the variables and parameters are replaced by corresponding vectors and matrices referring to the complete set of elements present in a given system, then we get the performance equation of the primitive network in the form as the given. See here, the performance equation we are taken for only one element. If a number of elements are present, then we were going to replace this with its vectors. VPQ will be replaced with this vectors, like see, VPQ is the voltage between P to Q. Like that, many elements are there. 1, 2, 3, if an element is having more than 2, then we are going to give its own numbers, like voltage V12, voltage V21, voltage V13, V23, like that. Different voltages are available. All those voltages we can shown it in one vector. At the same time, EPQ also in the vector form. Then ZPQ, here only the self impedance of the particular element, which can be given a primitive matrix of the different elements, and IPQ also replaced by its current. So the equations will be now V plus E, that is the voltage vector, and EMF or your potential difference vector is equal to primitive impedance matrix into current vector in the impedance form. In admittance form, we can write it as current I vector plus current J vector is equal to primitive admittance matrix Y with voltage vector V. A diagonal element of the matrices of Z or Y. If the matrix Z is nothing but primitive impedance matrix and matrix Y is the primitive admittance matrix, so diagonal element of this matrix is a self impedance ZPQ PQ or self admittance Y PQ PQ. Here the twice PQ PQ is considered because it is called as self, means from element 1 2 is, for example, we are considering element 1 2, the admittance or impedance which is from 1 2 to 1 2, it is called as self admittance, so it is shown as ZPQ PQ. So all the diagonal elements are self admittance, means let us consider 3 element system. A primitive matrix is of order 3 cross 3 because element to element matrix it is. The elements, no, total elements of the matrix is what, like A11, A12, A13, A21, A22, A23, A31, A32, A33. Here A11, A22, A33 diagonal elements are nothing but self impedances or self admittances, and off diagonal elements like 2 1, 1 2, 1 3, 2 3, 3 1, 3 2, what are we are calling it as off diagonal elements, are the mutual elements. It is shown by PQRS, or in impedance matrix means it is ZPQRS, admittance matrix means it is YPQRS. So PQ is one element, RS is one element, so it is a mutual admittance or impedance values. The value present as mutual coupling between the elements PQ and RS, usually we are going to describe it. The primitive network admittance matrix Y can be obtained also by inverting the impedance matrix Z. Once if you know the matrix Z, you can get Y, or vice versa. If you know Y, you can get the Z. If there are no mutually coupled elements for the given system, the both matrices Z and Y are only diagonal. In such cases, the self-impedances are just equal to the reciprocal of the corresponding values of the self-admittance, vice versa. So let us see one example. Given that self-impedance of the element of a network fulfilled by the bus incidence matrix given below are equal to, means here total 6 element matrix is given. Here element 1 and 2 is having impedance of 0.2 per unit, third element is having 0.25 per unit, fourth and fifth element is having 0.1 per unit, and the sixth element is having 0.4 per unit. Draw the corresponding oriented graph and find the primitive network matrix. Neglect the mutual values between the elements, means only self impedance values are given. For the incidence matrix, see here they are given one incidence matrix. For this they are given the values of Z. They told that there are 6 elements. Okay, obviously by seeing this matrix we can come to know this is 6 elements and nodes are 3, means in incidence matrix, best incidence matrix means here reference node is not there, so we need to add one more reference node. Means here this network is having 6 elements plus 4 nodes. Nodes means one including one reference node, but the reference node is not given, but we need to get the reference node values. How to get? Adding one reference node to make total row as 0. So in the first line we are having only -1, means in reference node we have to add 1. In second one we are having only -1, in reference node we have to add 1. In third element also we are having only -1, so we need to add 1. Remaining 4, 5, 6, see here already sum of the row is 0, so no need to add 1 or -1 in the reference node, we can put directly 0. The same thing I have got here, cap matrix or A cap. See 1 -1, so first column is taken as reference 1. So now we got the A cap or incidence matrix. From that we are going to draw the oriented graph. See here first element is connected between where to where, from 0 to node 1. See here 0 to node 1 first element, second element is 0 to node 2, see 0 to node 2, and the third element is 0 to 3, see 0 to 3 in the red color what I have shown. Then remaining 3 elements is 1 to 2, see fourth one is 1 to 2, fifth one is 2 to 3, fifth one is 2 to 3, and sixth one is 1 to 3. See we are going to get the oriented graph from the A cap matrix. So they are given the values Z1 to Z6, no, in the problem previously. We know there are 6 elements. As I told you, 6 cross 6 is the matrix form. See 6 in the row side, 6 in the column. Only self impedances is given, so all the values are diagonal only. See Z1 is given 0.2 there, Z2 is given 0.2, Z3 is 0.25, Z4 is 0.1, Z5 is 0.1, and Z6 is 0.4. Only in the diagonal form it will be there. There is no mutual value, so we can put it is 0 there. So as I told you, to get the primitive admittance matrix is easy from this one, because there is no off diagonal elements, all are 0. Just reciprocal of this Z will gives you the primitive admittance matrix. See all these values are primitive admittance matrix. Only diagonal elements are present because only self values, there is no off diagonal values, no mutual values. So this is the primitive admittance matrix without having mutual coupling. Let us check one example with the mutual coupling. See here 3 elements are given with the 3 bus, but mutual coupling are there. See first element is connected between node 1 to 2 and it is having its self impedance value is J4.452. Second element is connected between 2 to 3, its having impedance is J.387, but this element is having one mutual element with element 1 2 with value J.165. Fine. Third element is connected between 1 to 3 having impedance value J.619. It is also having one mutual impedance with the element 1 to 2 with value J.234. How to write this one? See, as you know, only 3 elements here. The matrix is of 3 cross 3. See, first element is 1 to 2, second element is 2 to 3, third element is 1 to 3. Same as in your columns 1 to 2, 2 to 3, 1 to 3. Self values are given. See, first 1 to 2 is having 0.452. Same thing I have kept in first diagonal value. Second diagonal value is 0.387. See, 0.387, and third diagonal value is 0.619. Coming to the mutual values, see here 1 2 is having one value, mutual value with 2 3, means it is 2 3 is having value with 1 2, as well as 1 2 is having value with 2 3. So I have written that 0.165 is in element 1 to 2 to 2 to 3 also, 2 to 3 to 1 to 2 also. Same time, element 1 to 2 is having one more mutual value with 1 to 3 with the value 0.234. Same thing I have drawn here. 1 to 2 is having a mutual value of j 0.234 with 1 to 3. At the same time, element 1 to 3 is having one mutual element with the value j 0.234 with element 1 to 2. And remaining 2 to 3 is not having any mutual value with 1 to 3, so those two things we keep it as 0. This is what the primitive matrix of given this table. So this is what the primitive matrix, primitive impedance matrix and primitive admittance matrix. If you want the primitive admittance matrix of this one, we need to get the reciprocal of, or we need to get the inverse of the element set. We cannot write directly reciprocal here because off diagonal value is also present, so we need to go for the inverse of this matrix, that to get the primitive admittance matrix Y. Thank you.